Let's get going here. Okay, so those are our assumptions we're going to start with. That the, oops. There we go. A little clearer there. Okay, so what is the shape of our sound beam? Yeah, this shape, and it's over there on the back wall if you're ever interested. It's always the same. We always show it as coming into like a sidewall, excuse me, sidewall back there. Yeah, it's just up on a piece of paper back there. We have a point that we call the focal point. We have a near zone, which is everything from the transducer to the focal point. Okay? That's the near zone. Then we have a far zone. Okay? And there's an area around the focus that we're going to call the focal zone. Now, what defines the focus? That's where the beam is absolutely the narrowest. And coincidentally, I don't know if it's coincidence or not, the focus is 1/2 the width of the initial beam at the transducer. Okay? So how wide is the focus? Well, remember that drawing I had of the diameter of the crystal? It's going to be half of that. D over 2, right? Diameter divided by 2 is the focus. I'm going to go grab something. I'll be right back.
Yeah, exactly. No. It's less than it was, but.
And I don't have any supplements or. I don't believe I have chronic sinusitis and so I know. But I'm not, I don't feel stuff. Yeah. But I have tons of allergies to the outside. My cat's all first. I go and pet her on his inside. I love you, but I hate you. No, I love her, my body hates you. Other than stuff I'm ready to hold. I just have one of these.
All right, so I've got a cute little toy for everybody. Sasha, you'll have to come by and pick yours up. Yeah. So let's talk about the near zone. The near zone is this area between the transducer and the focal point. And that's where the sound is naturally focusing down. We call it the near zone or the Fresnel zone. And it's just this area between the transducer to the focus. I have enough of these for everybody, so just be patient. What I'm handing out are called Fresnel lenses. Okay? And these are cute little lenses. Sometimes you see them on the back of RVs. You'll see just a flat piece of something like this on the back of the RV, and what it does is it lets the driver of the RV see a wide area behind it. Has anyone seen something like that? Yeah. Well, these are Fresnel lenses. They're flat, and what makes them lens is these little cuts that are in them. So you can put these in your wallet or whatever. But now you have a Fresnel lens. Okay, just like your transducer essentially has a Fresnel lens, and it lenses the sound into a focal point by interference patterns between so it lenses the sound down because of interference patterns, and that's what's happening with the light in these little lenses. is it's causing interference patterns, which in this case magnify the light, and in our transducer, the interference patterns cause it to focus down. So if you have trouble reading, you can use one of these to put on your paper and read a little better. Yeah, they work. They really do, and they're flat, they really are.
When you look at the screen, it's upside down.
Well, yeah, it's like any lens or magnifying it. There's some point where it focuses and then crosses, right? Yeah. Okay. All right, so that's Fresnel effects. Fresnel effects is what cause the focus to occur with an ultrasound beam. All right? Now, the focal length, or focal depth, or depth from the transducer to the focus, the distance, can be calculated, but I'm not going to throw that at you right now. We'll wait just a minute. Okay. And so the focal depth is also called the near zone length. That's probably what we typically call it, the near zone length. That's the most common. If you hear the term Fresnel length or focal length, those are all equivalent terms. That's just the distance from the focus to the transducer, from the transducer to the focus, however you want to talk about it. Now we have something called the far zone. I don't have a cute little plastic lens or anything for the far zone. This is known as the far zone, the far field, the Fraunhofer zone, or the divergence zone. Okay? And this is where the beam diverges. It gets wider. It's past the focus. It goes from the focus to infinity and beyond. Okay? It just goes forever, and it gets wider and wider. Okay? One of the cute little things about ultrasound, I need to go back a slide, is when you look at the focal length, the distance from the transducer to the focus, okay, it starts out at a diameter D, right? Starts out at D, and then it goes down to 1/2 D at the focus. We already said that, right, when we talked about the focus. Goes to 1/2 D. And then, if you go that same distance from that you went from the crystal to the focus, and you go the same distance, the beam is again, has a width of D. So it goes from D to D over 2 to D again. Okay, so it's symmetrical, more or less symmetrical, all right, which is kind of nice. And so when I say it's kind of nice, it makes a really good test question. When you say, how wide is the beam at a distance of 2 focal zones, right? You go, oh yeah, it's just D, whatever D happened to be. Okay. So at 2 NZL, near zone lengths, the beam diameter is equal to the crystal diameter. And to me, it's just a coincidence that that occurs. I don't know why it occurs. It's just divergence and Fresnel all work together, and that's what you get. But it is a coincidence. It does occur, and that's it. Okay. Beyond that distance, beyond 2 NZL, 2 near zone lengths, it just keeps diverging and getting wider and wider forever. Okay. Now, we also have an area in our beam called the focal zone. Yep, there it is, focal zone. So the focal zone is this area around the focus that is good for imaging. That's how your book defines it. Area around the focus that's good for imaging. And that's not a bad definition. It works. So it's the region around the focus that's good for imaging. But there's a better precise definition of it that the book doesn't go into, but I will for you. It's defined as the area beginning where the beam is at least 1/2 the maximum intensity. Okay, where it gets to 1/2 the maximum intensity. Now remember, maximum intensity is at the focus. That's where the beam's the narrowest. So when we hit 1/2 maximum intensity, we've entered the focal zone. And then it goes up to maximum intensity at the focus, and then as the beam starts to diverge beyond the focus, we start losing intensity, right? Because the beam's getting wider, and when it hits 1/2 intensity past the focus, that's the end of the focal zone. Okay? That's it. So in the focal zone, you've at least got 1/2 the intensity of your beam all the time. All right? It's considered a good area for imaging. That's where you want, that's the sweet spot. Okay. So when we talk about the beam shape, okay, so the question is, explain this second point under focal zone, which is the focal zone is defined as beginning where the beam strength is 1/2 maximum intensity and ending where the beam is 1/2 maximum intensity in the far zone. So let's take a quick look here at this. All right. So if, oops, and we look along our beam path here, okay, we have a point that is the focus, right? At the focus, we know that the intensity is maximized, right? Because the area is minimized, the intensity is maximized. All right. At some point in front of that, oops, wrong button. I don't know how to do this. Okay. At some point in front of that, there we go. And behind it, there's a place where, oops, wrong button. There's a place where the intensity is 1/2 the maximum. Okay? And that's because the area is either wider and then getting narrower, or it was narrow and getting wider. So there's some point where there is intensity at 1/2 of the max. That defines the start and stop of the focal zone. Okay? And it turns out that that's just a really good area for imaging. Everything in there is, the beam is pretty darn narrow in that area. Okay? So life is good, you image there, and it's all wonderful. Do we have to measure that? No, we don't measure it. But we should know that it exists. And it's defined as where the intensity is 1/2 of the maximum. Okay. So this is the focal zone.
So on the machine, when we're moving our focus at or just below where we actually want to see, it's so we are getting the maximum in, like, focal zone? Is that,
Yeah.
because we're going to.
Yeah, we're getting the maximum focal zone, but when we are using the machine and we try to move that focus just below the area of interest, or at or just below, what we're doing is we're imaging then with the near field. We're doing all of our imaging with the near field. Okay? And that is the best for imaging. For making pictures, is if you're imaging just in the near field, it's all the more gooder. All right? And so that's why when we go from in here, the theoretical thing is to image in the focal zone, because that's what the physicists will tell you. When we step into the lab and Brian takes off his physicist hat and he puts on his clinician hat, I move the focal zones down to the area of interest or just past, because that makes a more gooder picture. Okay? And it's because we're imaging then in the near zone. Okay? And more of our image is focus. More of our image is focus when we do that. Now, is there a perfect place to have your focus according to a physicist? Probably. If you're scanning and you're doing real scans for real people, it's best to have it just at or just below your area of interest because of that, because that's the practical way to do it. Yeah. You all good now? Okay, so let's end there. Here's the summary, okay? At the transducer, the beam is equal to the size of the transducer. That should make sense. At the focus, it's 1/2 the size of the transducer, the diameter of the transducer. At 2 near field lengths away from the transducer, it's back to the same size as the diameter of the transducer. And then beyond 2, it just gets bigger. We good with that? It's not complex. It's a very simple shape. We just have to know a lot of things about it. Why the heck is the beam shape so important? Huh? Why is it so important to know the shape of the ultrasound beam?
So we know where we're concentrating the picture.
So we know where we're concentrating our energy. That's a good point. Yeah.
If we want to do fine needle aspirates?
Yeah. I think you're getting there, but yeah, not quite.
Well, if you change the diameter of the transducer, the focal zone gets like double as small.
Right, yeah, we can change the diameter of the transducer and move the focal zone around and change its size.
So we know where that sweet spot is?
Yeah. Not so much so we know where the, so it turns out that the beam width, the beam shape, is your lateral resolution. Okay, so we've talked about axial resolution a little bit in the labs, right? It's your ability to separate dots along the path of the beam. And I think our next chapter we get into lateral and axial resolution. But the beam width is the lateral resolution. It's your ability to separate structures side by side. So that's why it's so darned important, is because that's our resolution. That's it. And we really need to know, you know, the beam size. It's important. Okay. Okay. So the beam becomes, when we create a sound beam, it emits from the crystal. It gets progressively narrower until it focuses down. This is called the Fresnel zone or the near field. At the focus, it's 1/2 the diameter of the crystal. Okay, the focus defines the end of the near zone. Okay? So that's the distance from the transducer to the focus is the near zone length. The far zone marks the beginning of divergence. So the beam starts to diverge at the far zone. At twice the near zone length, the beam is the same diameter of the crystal. And then it continues to diverge forever and ever. I think we've sung this like 3 times now. Okay. So how do we determine the focal depth? All right. Now, if you use that old transducer that I had with the old machine, it's set by the manufacturer, so you don't have to worry about anything. It's like you have a focus at 5.2 centimeters, and that's it. You're done. Our new machines, we can adjust the focus, but let's just, in general, talk about the focus a little bit here. So, the systems where we can adjust the focus, today's systems are all called phased array transducers. Okay? The early systems, like the one I have, is a fixed focus. So focal depth is determined by, in a fixed focus system, those single crystals, the focus is determined by the transducer diameter and the frequency of the sound. So what determines the speed of sound in the media, right? The stiffness and the density, right? We know that. Well, here it is. What determines the focal depth? Transducer diameter and the frequency of the sound.
Same at the end of the focal zone?
All right, so very important, the focal depth and transducer diameter are directly related. The bigger your diameter, the deeper the focal depth. Okay. And it turns out it's related by it's squared. Okay. If I double my diameter, I increase my focal depth by a factor of 4. If I triple my diameter, I increase my focal depth by a factor of 9. Okay. And focal depth and frequency are directly related. If I increase my frequency, I increase my focal depth. Now, I hope that some of you are thinking that doesn't make sense. If we increase our frequency, we shouldn't be seeing deeper. Well, yes, attenuation goes up with increased frequency, but the focusing gets better. Okay? So we can focus deeper, but we lose all our signal. So, yeah, oh well. Okay, so here is your equation if you want to learn the equation for focal depth. Focal depth in millimeters is equal to the diameter of the crystal squared times the frequency divided by 6. If you want to learn it, but you don't really care about frequency, you want to learn it based on wavelength, then it's the diameter squared divided by 4 times the wavelength.
Which is better to learn? It doesn't matter? Just one.
They're the same.
Yeah.
They're exactly the same. Yeah.
So on an image with like the focal depth, when it changes the focal depth, like, so that it slides up and down, right, kind of, like, that makes sense?
Yeah.
Like looking at an image, so your focus is always gonna be, how does it, cause it tapers down, right?
Right.
But when we set our focus on a machine, typically our image is like this, and that focus, it pretty much clears up everything, that whole section. So how does that work, since it's kind of like the tapering's reversed on the image versus the being.
I'm gonna try to draw a picture, but I'm just gonna preface it by, I'm not exactly sure what you're talking about, but I think if I draw a picture,
Yeah, sorry.
it'll make sense to all of us. Okay, so if this is our, okay, so this is our typical picture, right? Something like that, okay? When we send out a pulse, and I'm going to just send it out from the center of the beam here, and we'll make it red just so we can see the difference. Okay, so here's my pulse. I'm going to start out by just firing it off in the center. And what happens is we create a single scan line with a single pulse. Okay, we talked about that before, right? So this pulse is going to travel down here, and we're going to get echoes back along it, right? And the shape of the pulse is going to be something like, that's not the best shape. Let's see if I can do this without, there. So the shape of that pulse, it's going to come down, it's going to narrow down, and then it's going to spread out. And then on our next scan line, we might come over a little bit. Let's do it in blue this time. And do one over here. Okay? Does that answer your question?
Yeah, that makes sense. For some reason, I'm
Yeah.
thinking it as like the whole thing.
Right.
It has like one foot, I'm like, okay. But
Right.
this makes up like
Each
a-
pulse is going to create
Yeah.
its own scan line. Okay? And unlike my drawing, they would be much more consistent than, they're going to look the same as they go across. I'm not very good at drawing, so mine look like the focus is all at different places. Yeah.
So by manually moving your focus,
Yeah.
how does that change what the beams look like?
Yeah, so what adjust our focus is we're doing a couple of things. And I'm just going to draw my crystal up here this time. And so we've already said that we can change the focus by changing the diameter of the crystal, okay? Or the frequency. So we're not going to change the frequency, we're just going to change the diameter. And what we get with this one, let's do it in blue here, with the little one is it focuses down and then it spreads out, and that gives us a focus right there. With the larger one, it's not going to focus down until it gets deeper into the body. Okay? So when you're changing the position of your focus, the position of these little carrots, you're effectively changing the diameter of the crystal. All right? And so let's go back to our picture of our slide here. And you can see that I've got a little crystal, and it's going a short distance and then diverging, and a bigger one that's going a deeper distance and then diverging. So we're changing, when we change our focus, our position of our focus, we're really just changing the diameter of the crystal we're using. Yeah.
So the piezoelectric crystals are not solid.
No. No. Each crystal is solid, but we're using something called a phased array crystal in this. So just a couple slides ago I said that the adjustable ones are phased array. Okay? So we haven't talked about what a phased array is yet, and it's on page 169 of your book if you want to jump ahead, but we'll get there. We'll teach you what phased array is. We just don't want to jump. We have a lot of vocabulary to build before we get there, and so that's what we're doing. Okay? So if you imagine the little carrots that form the image, we're just taking this and we're saying, here's a small crystal. It's going to focus very close to the diameter, to the crystal, and then it's going to spread out. Here's a bigger one. It's going to focus deeper. Okay? All right. All right, so again, we have the clinical dilemma. If we want a deeper focus, we could increase our frequency along with increasing the diameter of the crystal. So we could increase. But what does that cause for us?
Smaller like a closer focus.
If we increase our frequency, what happens when we try to scan deep?
Attenuates?
It attenuates, right? More of the signal is absorbed, and so we lose our ability to see anything because it all becomes attenuated, okay? So it also says, but we typically use very high frequency to see structures that are close to the transducer, right? So if we increase our frequency, it causes the focus to be different. How do we focus closer to the skin? Ingrid?
Don't you just use a different transducer?
Yeah, basically. How do we get that higher frequency focus to be closer to the skin?
Change diameter.
Yeah, change the diameter. Make the diameter smaller. Yeah, exactly. Okay. So with short little diameters, you can see that the focus, if we make the diameter smaller, the focus moves from here inward, okay? If we make a higher frequency, then the focus moves back outwards. You just got to trade off those two things.
So the, you can just use fewer crystals?
Yeah, you use fewer crystals, exactly.
Okay.
And we're gonna end up calling that the aperture next week, or probably Friday. But yeah, fewer crystals to shorten the diameter. Okay. All right. Sound beam divergence. Okay, so we talked a lot about the focusing in the near field. Beyond the near field, the far field, the sound beam diverges, and the angle of the divergence depends on the transducer diameter and the frequency of the sound, coincidentally. Same thing as everything else depends on, right? So the angle of the divergence, and you can see I've kind of measured these angles of divergence. When you have a bigger crystal diameter, that angle of divergence is much, much less than when you have a small crystal diameter. We good with that? So if you're trying to image in the far field, right, deep, which is going to be better? A wide crystal, a large diameter, or a small diameter?
Large.
Right, large. How about for the near field? Small, yeah.
Who cares?
Well, a lot of people. Just depends on what you're looking at. You know, if you're looking for lymph nodes in the neck, you want to be able to look at that near field very clearly. If you want to look at the aorta deep inside of Mrs. McBurger, then you're going to have to look with a deeper transducer, right?
focal zone.
I guess I was thinking that if it attenuates very quickly, then you might not ever see the evidence of the lower
Right.
angle.
Yes, you're absolutely right. And attenuation is another trade-off that is made with ultrasound, so yeah, it kills our signal. Okay. So crystal diameter and beam divergence are inversely related. The smaller the crystal, the greater angle of divergence. The larger the crystal, the smaller angle of divergence, which leads us to this conclusion that larger crystals give us improved resolution in the far field.
It's just a repetition with different words, I believe.
Yeah. But I took it straight out of your book. If you read the book, it's like every other page is identical with different words. I mean, it's just the same thing restated half the time.
You said better resolution.
Better resolution in the far field with larger diameter crystals. So now we're going to go to a new page, and guess what? Just a restatement of the last page, pretty much, just a different way, right? And that should make sense.
You let us know how you felt about the book before we started. It's okay.
I did, but I got another book if you want it. You can read it. You know, I don't know what you want. Do you want more information or less information?
The one that's gonna give me the answers.
Yes, yes.
What?
The one that's gonna give me the answers to like pass the test, that's what I want.
This one will give you the answers to pass the test.
Perfect.
The other one will teach you how to build an ultrasound machine.
They hire people to do that,
There's
right?
no in
That's
between.
not my job.
No, there is an in-between one. So
This one's good.
the Kremkow book will show you pictures of the building of an ultrasound machine.
Oh,
So-
I came across that.
Did I tell you the guys the joke about the three guys that wrote the physics books?
No.
Okay, so the three physics books that are most commonly used are Edelman's, which you have, Mealy's, which is the one I've always liked because I like to know how to build the machines, and then Kremkow. Dr. Kremkow is the third author that is most commonly used. His book is filled with pictures. So the joke goes, if you ask Edelman what time it is, he will tell you what time it is. If you ask Kremkow what time it is, he will show you his watch. If you ask Mealy what time it is, he will teach you how to build a watch. So that's the joke about the physicists that write the books. I'm trying to balance Mealy's with Edelman's, with Kremkow's to show you pictures, make it understandable, give you enough information to pass the registry exam without overwhelming you with details that you really don't need to know. And believe me, there are plenty of details that you don't really need to know. Okay, so sound beam divergence. Frequency and divergence are also inversely related. So we talked about diameter and divergence are inversely related. Frequency and divergence are also inversely related. Lower frequency, greater angle of divergence. Higher frequency, less angle of divergence. Okay. So higher frequency improves the resolution in the far field. Doesn't help with signal strength, trust me. Signal strength still is bad, but it improves the resolution. Yeah.
So is the crystal diameter and frequency, are those directly related? You may have gone over that already, but you just said that crystal diameter and beam divergence are inversely, and so is frequency and beam divergence?
They're both inversely related. So let's go back to one
So
slide.
I'm just wondering if crystal diameter and frequency are.
Crystal diameter and frequency are not related,
Okay.
okay? And that's where a lot of people make a mistake. Crystal diameter and frequency are not related. They both contribute to the shape of the beam, but they're not related. What is related is crystal thickness and,
Frequencies.
and frequency.
Okay, thank you.
Yeah. Let's go to voicemail. There we go. Okay. All right. Now, if you want to know how to calculate beam divergence, here's your equation. The sine of the divergence angle is equal to 1.85 divided by the diameter times the frequency. Okay. Another way to restate that is the sine of the divergence angle is 1/2 of the wavelength divided by the diameter. Which one of these do you think you need to know? Neither one.
I don't know
Okay.
what a sign is.
You don't know what a sine is? Oh, okay.
Cosine,
I don't know much about it, but.
theta.
Do I have to explain sine?
Tangent. Sure.
Okay.
All I heard is that I don't.
Trigonometry.
Yeah,
Yeah, it's trigonometry.
it's trigonometry. So,
So
That's okay,
opposite
you really, I
over
mean, we don't need it,
hypotenuse.
you don't.
well, I'll just show you real quick.
No,
All right,
opposite
so if
over-
you have an angle, let's
So
get
Katella.
this off of there. If you have an angle between two lines, right? So here is my angle, we'll call it, oh, let's be creative, we'll call it theta, because I always call them theta. Now, if we take this line and we drop another line straight down to it, then we have this side opposite here, opposite our angle. We have this side, which is called the hypotenuse. I'll just call it hype. And then this one is adjacent to our angle here, so we'll call that adjacent. Okay, so the sine equals the opposite length over here divided by the hypotenuse. Okay? So it's a trigonometric relationship between the angle and the length of these sides. That's all it is. The important one for us is going to be the cosine, and so cosine is going to equal the adjacent divided by the hypotenuse. Okay? And then there's one other, there's the tangent, that's the opposite divided by the adjacent. We don't need to know that one. So those are the trigonometric relations with this angle.
Which, symbol do you use for cosine?
COS.
Okay.
So I always cosine, I just wrote it out there, but yeah, COS is the standard math symbol for cosine. Sine, sometimes they write it out with, throw the E in there, but sin works for it also. So, yeah. To this, all right, let's move on to spherical waves. So, yeah, you don't need to know these equations. They're just useful information, I suppose.
Fun fact.
If it helps you, though, knowing that the diameter and frequency are inversely related to the angle, then, you know, these are good to know. But otherwise, you don't need to know them for anything. Did we already cover refraction? Yeah, we did, didn't we? Yeah. Refraction is governed by Snell's law, right? And that's the only other time you're going to see signs in ultrasound physics is with Snell's law. And we don't really need to know it for that, but it's very useful. Let's talk about spherical waves for a second. Okay. So these are known as wavelets, or little tiny waves, or Huygens wavelets. And what happens is what happens is these small little, if you get your transducer crystal small enough, okay, imagine it being really small. When it vibrates, it just sends out what essentially is a spherical wave. Okay? So we would call it a point source transducer. Okay? So it has to go out in a spherical wave because there's no flat surface to it. So we've made it. Do I need to draw a picture of this?
Yeah.
Okay. So let's take our typical transducer. Okay. Now this thing is big enough that the wave starts out and then it'll focus down and then diverge, right? Well, if we make our transducer smaller than that,
You're not drawing anything.
oh, I'm not, there. If we make our transducer smaller than that, we already discussed that this will cause it to focus down and then diverge quicker, right? Okay. Now, imagine if we make it really small, okay? All it's doing is diverging from this point on. Okay. And if you wanted to, you could actually say that it's doing like that. It's just making a circular spreading out of the wave, right? It's so small that all you're seeing is divergence. Okay, we're going to call that a wavelet. Okay. Now, where this becomes useful, oops, if I take a whole bunch of, let's say I take a big old transducer, I'm gonna make it, I just turned it on the side, so it's coming down from the top this time, okay? And we're going to take this piece of piezoelectric material and cut it into little bitty microcrystals. Okay? So we've just chopped up a nice big single crystal transducer into a whole bunch of mini crystals. All right, so let's take our mini crystals, and we're actually going to hit these with a little bit of electricity, okay? So let's just, okay, that represents a wire going to the crystal, the mini crystal, with a little pulse in it, little pulse of voltage in it. That's what the little, if I did it better, it would look like, that's how most people do it. They do it like a little Z looking thing, a zigzag. Okay, so that's a little pulse of energy. That pulse is that ringing of the bell, right? So when I ring the bell, that's what I'm doing. I'm hitting it with a pulse. So when that pulse gets to the crystal, it starts ringing. So let's draw one. Oops. Closer, and then this one right at the transducer. So this one is at the transducer, and it starts ringing. Okay, and it's going to form a little wavelet. Now, a little bit later, this next pulse gets to the transducer and causes this one to ring, right? but it's a little later, so the first one has moved. Okay, here we go. So the first one has started to come out here when that second one rings. And then a little later, we have the third one right there, and it's going to start ringing. And when it does, then the second one has moved on, and the third one is even farther out, right? And so you can imagine this continuing on for quite a while, as many of these as we want, and you'd end up with all these little wavelets. I want to redraw this. Oh well. We'd end up with all these little wavelets forming a wave front. Okay? So that's what the little wavelets are for. We can create a wavefront with that. And the really cool thing is that this wavefront will move in a direction perpendicular to the front. So we've just taken a transducer with no moving parts and found a way to move, to steer our beam. Okay? So that's what the wavelets are for. So let's go back to our book and talk about these wavelets. So these little wavelets are really you can see these little, they did a much better job here. You can see these little crystals in this, the GIF or GIF? GIF up in the corner there.
GIF.
Yeah, and it's causing waves to be created and forming a bigger wave. Okay. Nicole, you're shaking your head no. What?
Oh, she was asking me if that's similar to like a matching layer, but I was.
No.
Is it kind of reminding me of like the stair steps, so I
Yeah,
don't know if
no.
it was-
These are not the matching layer. These are just little individual crystals that are firing off at different times. Okay? That's what a phased array transducer is. Okay? That is what we use to make our pictures. It's a phased array transducer. Phasing means different times. Okay? I know the book says phasing means something else. But phasing literally is an electrical signal shifted so that it's at a different time. Okay? That's what phasing is. And they arrive at the crystals. The crystals fire off at different times and form a wavefront that then moves through the body. This idea that you can take little wavelets and create a wave, a single wave out of them, is called Huygens principle, or Huygens effect. Okay? And so you're probably thinking, Huygens sat there and dropped a lot of pebbles into water and observed the waves. Well, that's not what he did. Huygens was an astronomer, and he figured out that the rings around Saturn were made up of little tiny crystals that were reflecting light, and it made it look like solid rings. So if you ever get a telescope and you look up at Saturn, which is a really cool, fun thing to do, by the way, and you see those rings, they look solid. I mean, they look absolutely solid, but we know that they're made of just little ice crystals. And what has happened is they're each reflecting a little bit of sunlight, and it makes it look like a solid ring around the planet. Really cool stuff. So that's what Huygens studied. He found this Huygens effect, that if you take small little wavelets and add them together, you get big waves. There you go. So wavelets emitted by small sources can add together and form a wavefront. That's tough.
So, but the image that we pick up and show on the screen is created by the wavefront, not the little, well, essentially, I guess the tiny waves too, but.
Yeah, so she said the image that we see on the screen is created by the wave front. She's absolutely right. Okay, when we see this little wave being created on this image here, it's being made by a whole bunch of crystals creating a single wave pulse that then moves through the body. Absolutely. When we look at these interference, by the way, this is near field effect here.
That is pretty.
So these interference patterns, this is a bunch of little wavelets firing off at once, creating a single wave. Okay. So near field effects, this stuff, right, the little magnifying glass, are created by interference patterns within the crystal, that the crystal makes. So these near field effects will focus the beam down for us. And you can see that beam forming on the left there, and it really does focus down quite a bit. Okay. So really well focused beam. You can see on these are plots on the right. We're seeing plots of the amount of energy at different points in the beam. And so the brightest spot is the focus right in this area, and then it diverges out and drops. Okay. Yeah.
So just a question, over on the left, when it reaches the focal point and then it crosses over, that's why this flips?
Yeah, yeah, yeah. So so she says on the left, the beam is focusing down, and then it crosses over, and that's why it flipped. If you look at your magnifying lens at a distance, everything's upside down. Yeah, more or less. With sound, it doesn't flip though. It's focusing and then diverging. But if you want to think of it as flipping, that's fine. I'm not gonna try to change anything there, because it acts like it flips, right? That's fine. Perfect. Good analogy. All right. Okay. So that's everything you need to know about sound beams. It's not that hard. It is a lot of vocabulary, okay? It is a lot of vocabulary, but, I mean, it's so simple. They start out wide, they get small, and then they get big. And there you go.
Why can't the test just be like that? Draw me a picture of a sound piece. Okay. There we go.
Well, that would be a great question. So what if I said, on a test, if I had something like let's see here. So what if you had something like this on the test book with no labels, and I said, label this picture for 10 points. Right? You would be able to label the focal zone, you could even draw in the little things, focal zone, near zone length, twice the near zone length, diameter over 2, right? Thickness of crystal, diameter of crystal. You could do all that, right?
Yeah.
Right.
Hint, hint, wink, wink.
Yeah. Wink, wink, yeah, yeah. That would be a really good thing to know, you know? Being able to label this completely would be a really good thing to know for a test. And you might even see like what if you were just given like a pulse with a rest period and then another pulse? Could you label that completely?
A second time.
I don't know. Would it be the second time? For a lot of people, it'd be the first. You know? But that's what all this is based on. You know, the pulse echo technology and then the beam shape. If you know both of those, you know at least 75% of the test. If I double my frequency, what happens to my near zone length? Huh? If I double my frequency, how does my near zone length change?
Double your frequency, your near zone length. Well, it increases the resolution of the far field. You can't increase your
Yes,
frequency.
yes it does.
Yeah, it's even-
So, your resolution's gonna be worse than the
Be half.
near field?
If I double my frequency, what happens to my near zone length?
Half.
You need a smaller,
It gets shorter.
a larger diameter.
Okay, this will help you. If I double my frequency, what happens to the near zone length?
It will double.
It will double. Yeah, it will double. If I double my crystal diameter, what will happen to my near zone length? Say that louder.
Quadruple?
It will quadruple. It'll go up by a factor of 4. Yeah.
When you say the near zone length, where is that again on like the actual picture?
So
Like
near
the-
zone length is
From the focal to the crystal, right?
from the crystal to the focus. Absolutely. From the crystal to the focus is the near zone length. Let's see if we got that picture somewhere here. There you go. We call it the focal length on this picture.
How many exams do we have in this class?
3. 3 exams. We have 2 midterms and a final.
Oh shoot, I forgot it's just
Yes.
Can you go to the shape of the sound beam one?
What is it? Okay.
Under the focus, can you explain the second dot again, the point under defined as beginning where beam
Okay. Yeah. So